Well, here in chapter 3, what we're going to do is learn about two brand new functions. We know everything about a linear function because those are the ones in y equals mx plus b, where we can get a slope and a y-intercept, and the slope is, the rate of change is always constant on a linear equation. And then we know a lot about a quadratic equation, the quadratic being the y equals x squared, the parabola. So we're going to introduce two new functions. One's the exponential function, and one is the logarithmic function. So if we look here at the first one, which is the exponential function, I want you to take note of where the x variable is. You see how it's just right up here in the exponent? Well, it's because instead of now just saying like y equals x to the first, the linear, or y equals x squared, the quadratic, we now have our x, instead of being in the base, it's in the exponent. And that's what's making this an exponential function. Okay? Now we have two conditions here. One is where the base number, so like y equals 2 to the x, if the base is larger than 1, so for example, like I said, b equals 2, b equals 3, you can even go, the base could even be like 4.5, okay? So if the base is any number larger than 1, what the graph's going to look like in general is they always go through the point 0, 1. So remember, if you plug in x equals 0, 0 is an exponent, no matter what your base is, always comes out to be 1. So that's where that point's coming from. Another point you also might want to know about is the fact that when you go over to 1 on the x-axis, how high it is depending on your base. So if the base is 3, then it's going to be over 1 up 3. If the base is 10, it's going to be over 1 up 10. Okay. The second condition, oh, by the way, real quick, if you look at the domain and range, the domain is all real numbers. So no matter what, I can always plug in any kind of number for my exponent. It could be positive, it could be negative, it could be fractions, it could be anything. And that's what the domain's saying. Now the range, though, is what comes out are all numbers graphed in quadrants 1 and 2. So it's all these y values that are positive. And then what we have as a result is this we have this y equals 0, and this is a horizontal asymptote on the graph. Okay, kind of talk about it more over here, but it's a boundary line saying basically that the whole entire graph is going to be graphed in quadrants 1 and 2. Okay, now the second condition is where your base is less than 1. I want you to add in a little something right here. Okay, this technically should be 0 is less than b, which is less than 1. Okay. So we have a condition. Your base is, it's always going to be positive. Your base will be. It's just is that if it's going to be larger than 1 or it's going to be between 0 and 1. So numbers there would be something like b is 1/3 or 1/2, 2/3. Items like that are between 0 and 1. So if you have a small base, in other words, the only difference, you're still going to be graphing it up here in quadrants 1 and 2. It's just the graph is going to be coming down through the point 0, 1, as always. And then still over at 1, up at whatever your base number is. So if your base is 2/3, it's over 1, up 2/3. Okay, so those are still the same. And the domain and range is still exactly the same. Okay. And I put a little note on here that just in case, that if your base is positive, if your base is larger than 1, you're like, ooh, that's going to be the one that increases. No, we got to focus on that exponent. If it's a negative exponent, this is the same thing as going 1 over 2 to the x, which is 1/2 to the x. So, or a shortcut is when you see a negative exponent, make it positive and then take the reciprocal of your base. So make it positive and take the reciprocal of your base. So a negative exponent really is a base that's between 0 and 1. So 0 is less than b, which is less than 1. Definitely something to keep in mind. Okay, so all exponential functions, they either increase or decrease through the point 0, 1, and they are graphed in quadrants 1 and 2 with a horizontal asymptote right there on that x-axis. So if we do the kind of same thing, let's go to the logarithmic function. The logarithmic function is a little easy to identify because you have the whole word log written in there. And remember, the log function, when you see the word log, it's actually a function. Like if I told you to take, y is equal to absolute value of x, when you see these bars right here, you think, oh, I need to make everything in there positive. When you see this symbol, you think, oh, okay, if it was 16, you're like, what do I have to square to get this number inside? So now, whenever you see the word log, we got to think of something like that. Treat log as like those absolute value bars, or as like that square root symbol. It's actually a symbol, okay? It's not like something you can, if you're going to solve the absolute value of x is equal to 4, you can't just divide off absolute value bars. It doesn't work that way. Well, so if you're going to solve with log, you can't just divide off the word log. It's actually like a symbol itself. Okay? All right, now two scenarios we want to look at. Once again, where your base is larger than 1, and the other one where your base is between 0 and 1. Okay, so change that up to 0 is less than b, which is less than 1. If your base is greater than 1, again, the graph is going to be increasing. And this time it's going through the point 1, 0. Because the log of 1, no matter what your base is always 0. And this time, instead of going over to 1 and up to whatever your base is, we're going to go over to the base up 1. So it's direct opposite. What you're seeing is log functions almost are the direct opposite of exponential functions. If you see here, the domain this time is just the positive numbers, which was the range for exponents. The domain for exponents is now the range for logs. And that is a very neat tool in order to remember all of these. Okay. Up above, we had a horizontal asymptote, keeping everything in quadrants 1 and 2. Now we've got ourselves a vertical asymptote, keeping everything graphed is in quadrants 1 and 4. If your base is larger than 1, like I said, with like a 2, 3, or 4, or so on, we're going to increase through the point. And if your base is just between 0 and 1, so like a fraction, your graph is just going to decrease to the point 1, 0. Okay, so again, just some highlights on the log functions. And then specifically with logs, we have properties. Okay, we know we have properties for exponents. You know when to add exponents, subtract, and multiply exponents, and we know what to do with negative ones. We have the same kind of properties here with logs. And let's talk about this first property. Log base b of m times n. What it's saying is that if what you're taking the log of is a product, what we can do with it is we can break it up into however many things are in that product. We can break it up to a sum of each one individually. Notice they both take on the same base. It was where it was to begin with. It was log base b. So log base b of the first thing in the product plus log base b of the second thing in the product. And where this kind of relates to is if back in the properties of exponents, if I gave you an x squared and I told you to multiply it by x cubed. Okay, so if the bases are the same, and they're multiplied together, what do we do to our exponents? Well, we add them. Well, look here. If what you're taking the log of is multiplied, what do we do to the two? We add them. That's definitely not a coincidence. That was meant to be that way. The same thing here. Now, if we go to a division right in here, if I told you to take x to the fourth and divide it by x squared, we have a common base. Just like this, we have a base of b. It's common between both of those technically. And with the 4 and the 2, what do? We subtract them. Exact same thing. Okay? Now in property 3, all this property 3 is saying is what you're taking the log of, if it's in an exponential form, like say 2 cubed, then what you can do with that exponent is just take it from up here and bring it to the front. And that's what they're just showing right there. So whether you put that number in front that's being multiplied to your log, you can either leave it there or you can pull it back up as an exponent. It's the exact same thing. And 4 and 5, just log of 1 is always 0 because all those log graphs always go through that point, that 1, 0, whether it's going down through it or up through it. They all go through that point, 1, 0. And then what this is saying is that what you're taking the log of, if it's like the base number to any power, and right here, if the base for your log matches the base of what you're taking the log of, this all goes away and you just get that exponent right there. Okay? All right, let's go on to some other key facts. Let's talk about those for 2 seconds. Now, if you see the word log written and it doesn't have a base right there, in other words, the base is missing, you always assume it to be 10. Okay? This is the first time we ever assume something to be 10. Like if I gave you a variable by itself and I asked you what's the number sitting in front of it, you're like, oh, it's a 1. If I asked you what the exponent was, you'd be like, oh, that's a 1. Well, this is one of those cases where if something is not written, you actually assume it to be 10. And the reason why is that's what your calculator is actually programmed into. Everything your calculator does, even if you're adding 2 plus 2, your calculator is programmed to change that to something in base 10 and then add it that way. It's really kind of neat that way. But anyway, so always assume it to be 10. And then the whole idea, if you look on your calculator, you have a log button, and then you have this natural log button. It's like, what's the difference between a log and the natural log? Well, the natural log is one specific type of log. You know, when we talk about a log, and I said b, log base b of x, I said, well, b can be anything. If b is larger than 1, we got a certain type of graph. If b is between 0 and 1, we've got another type of graph. Well, if I specifically say, if I come in here and I say, I want that base to be this 2.718 specifically, which is e on our calculator, you can see it on your calculator. If you just look at it, it's that e that's right there. It's not like e, like the letter E when you're typing in something. It's the one that's right there behind the natural log button. It's in the blue written behind your natural log button. If your base is specifically E, then what you're talking about is natural log. So what a natural log is one very specific type of log. Okay? And the base for a natural log is always E. Okay. And last but not least, out of everything and anything that we are talking about right now so far, if you can remember this property right here, number 3, the way because obviously, hopefully throughout all of this, you've seen this great connection between logs and exponents. And this property right here shows you definitely the connection between logs and exponents, and how you can convert from going back and forth between the two. Okay, how you're going to do it, first of all, is if you're in log, look at the base. What is the base? Start there. Because the base for your log is also going to be the base for your exponential part. Okay? You go across the equal sign to get your exponent, and then what you're taking the log of is what it equals. So b to the y equals x. And the same way if you started on the right and wanted to go back left, what you would do is start with your base, write that down there as log base b. What it equals is your exponent, and what you're taking the log of is that part right there. Okay? And this is, if you're ever in a situation where you're trying to solve something and you want to get rid of the log, this is a way to get rid of the log. You just take it out of its log form and put it into its exponential form. And you can go that way with that rule, and you can go back that way with that rule, just as easy. Okay, well, let's start here with example 1. We want to graph y equals 1/2 x. So when I look at this, the first thing I notice is the fact that the base is obviously b is less than 1, still greater than 0, but it's less than 1. Okay, so I know that my graph is going to, if I go up there and look at my notes, I know my graph, first of all, is going to be up in quadrants 1 and 2, and that it's going to decrease through the point 0, 1. But how we're going to graph it, let's just pick some x and y values. So how about -2, -1, 0, 1, and 2? Okay. Well, obviously, let's start with the easiest one. 1/2 to the 0. Anything to the 0 power is 1. 1/2 to the first is just 1/2. And 1/2 squared is going to be 1/4. It's 1 times 1 and 2 times 2. All right, now let's look at this. I have 1/2 to the -1. Remember what I told you guys that was? Just change your exponent to positive and take the reciprocal of your base. So this is the same thing as 2 to the first, which is 2. Okay, if I have 1/2 to the -2, change your exponent from negative to positive and take the reciprocal of your base, and that's 4. Okay, so if we want to go up here now and take those points and put them all into a graph, okay, we've got 1, 2, 3, 4. Okay, we have the point -2, 4. We have the point -1, 2, 0, 1, 1, 1/2, and 2, 1/4. Now remember, as I connect these dots real quick, blah. Okay, not the prettiest graph, but y'all are getting the idea. You know that all exponential graphs go through the point 0, 1, so that checks off right there, and that they always go, if you go over 1, you always go up to the base. The base was 1/2, so that checks off right there. And the only other thing I'm going to add on there is the fact that when I graph this, I also want to always remember to keep drawing always that horizontal asymptote. So it's y equals 0. That's very much a part of the graph. All right, let's go on to example number 2.